Hello everyone, welcome to video tutorial class Dorong College e-learning platform. Today's video is meant for BSc BA 3rd semester SSC students, subject mathematics, paper combinatorics and graph theory. Today in this video we will discuss what is a Hamiltonian and Eulerian graph. Let's start. Before knowing what is a Hamiltonian and Eulerian graph, let us know what is a graph and some of the basic concepts of graph. So here's the definition of graph. A graph consists of a set of elements called vertices and a set of elements called edges. Basically, a graph is a set of collection of vertices and edges where each edge joins exactly two vertices. So let us understand a graph with the help of an example. In a graph, two or more edges joining the same pair of vertices are multiple edges. So in the example, the edges 3 and 4 join the same vertices W and V. So they are known as multiple edges. Again, an edge joining a vertex to itself is a loop. So here the edge 6 is a loop because the vertex X is joined to itself. Again, a graph with no multiple edge or loops is a simple graph. But this example is not a simple graph because it consists of multiple edges and loops. Here, U, V, W, X are vertex and 1, 2, 3, 4 are edges. Now let us know what's a walk. So consider a finite graph having at least one edge in the graph G or an alternative sequence of vertices and edges of the form Vij, Vi plus 1, Ej plus 1 up till Ek, Vm, E suffix k, Vm, which begins and ends with vertices. So we are considering a sequence, alternative sequence of vertices and edges, and the alternative sequence begins and ends with vertices. Let us know what is a walk. In a walk, a vertex or an edge or both can appear more than once. That is, a vertex or an edge or both vertex and edge can appear more than once in a walk. The above sequence, the above alternative sequence that we have considered, Vi, Ej, Vi plus 1, Ej plus 1 up till EKVM, is called walk sequence. Walk sequence always begins and ends with vertices. So a walk that begins and ends with the same vertex is called closed walk. Again, a walk that begins and ends with two different vertices is called open walk. That's the definition of open walk. That means if Vi and Vm are different vertices or different vertex, then it is open walk. And if they are same vertex, then it's a closed walk. Now let us see some examples of open walk and closed walk and also walk sequence. Here V1, E1, V2, E2, V3, E8, V6 is a walk sequence, alternating sequence of vertices and edges. So this arrangement is known as walk sequence, and here the n vertices V1 and V6 are different. They are different vertices, so it's a open walk. It's an open walk. Now let's see the second example. Here V1, E1, V2, E3, V5, E4, V1. So both the n vertices, it's an alternating sequence of vertices and edges. So it's a walk sequence, obviously it's a walk sequence, and V1 and V1, the n vertices are same. So it's a closed walk. Again, the third example, V1, E1, V2, E3, V5, E5, V3, E2, V2, E1, V1. Here, it's also an alternating sequence of vertices and edges, and the n vertices are same, V1, V1. So it's also a closed walk. Next is trail. Trail is an open walk in which no edge appears more than once. Let us see the above examples. The first walk sequence is an open walk sequence and all the edges are appearing only once, so it's a trail. But the second and the third sequence are closed walk sequence. It's not open, so they are not a trail. Circuit. Circuit is a closed walk in which no edge appears more than once. Similarly for circuit, but it should be a closed walk. Here in every sequence the edges are not repeating, but the first sequence is open walk, so it cannot be a circuit. But the second and the third sequence can be circuit. Since it is closed walk, the circuit should be a closed walk. Now let us see what's a path. A trail in which no vertex appears more than once is called a path. So for trail, edge appears more than once, but for a trail it should be open walk, and for circuit it should be closed walk. But for a path it should be a trail. That is, it should be an open walk sequence with no edge appearing more than once to be a path. It should be an open walk and no edge should repeat, or no edge should occur more than once. Now let's see simple path. A path is said to be simple if all the edges and vertices on the path are different except possibly at the endpoints. So to be a simple path, all the edges and vertices must be different except at the endpoints. So let's see the example here. The first sequence V1, E1, V4, E2, V3, E5, V1, alternating sequence of vertices and edges, and no edges is repeating, and no vertex also repeating except at the starting and ending point. So it can be a simple path. Similarly for the second sequence V1, V4, V3, V1, V2. So here V1 is repeating twice but not at the endpoints. In between V1 is repeated, so it's not a simple path. Okay, for the third example, V1, V2, V3, V4, V3, V1. In this sequence, V3 is repeated twice. Oh, it's okay. The ending and the beginning points, vertexes are same. The end vertexes are same, V1, V1, but in between again V3 is repeated. So repetition is not allowed. So it's not a simple path. Now let us know the main topic, that is Hamiltonian graph. So a graph should have Hamiltonian path and a Hamiltonian circuit. So these two conditions, Hamiltonian and Hamiltonian circuit, together gives Hamiltonian graph. So what is a Hamiltonian path? A Hamiltonian path is a simple path that contains all vertices of a graph G where the endpoints may be distinct. It can be a circuit in a graph G that contains each vertex in G exactly once, except for the starting and ending vertex that appears twice, is known as Hamiltonian circuit. And these two conditions, Hamiltonian path and Hamiltonian circuit, together gives us the Hamiltonian graph. If a graph has a Hamiltonian path and a Hamiltonian circuit, then we can say it is a Hamiltonian graph. Circuit was what? Circuit is a closed walk. Circuit is a closed walk. That means no edge appears more than once. A graph G is called a Hamiltonian graph if it contains a Hamiltonian circuit. Example, let's see the example here. So in example 1, we can find a Hamiltonian path. What is a Hamiltonian path? That contains all vertices of the graph. So here V1, E1, V2, E2, V3, E3, V4, E4, V1. All the vertices are covered. So it is a Hamiltonian path and it is also closed. So it is a Hamiltonian circuit. Hence, example 1 is a Hamiltonian graph. In example 2, we can directly see that the vertices V1 and V4 are not connected. So it is not closed. So we cannot get a Hamiltonian circuit. We can get a Hamiltonian path. All the vertices are covered, V1, V2, V3, V4. But it is not closed, so we cannot get a Hamiltonian circuit. Hence, it is not a Hamiltonian graph. So in Hamiltonian graph, repetition of vertices or edges is not allowed except at the end points, except the end vertices. Edges may repeat in some condition. In the second example, though Hamiltonian path is received, Hamiltonian path is V1, E1, V2, E2, V3, E3, V4. But Hamiltonian circuit is not received because it is not closed. So we cannot obtain a Hamiltonian circuit, though Hamiltonian path is obtained. So it is not a Hamiltonian graph. Both the conditions should be satisfied. Now, Eulerian graph. If a graph consists of Euler path and Euler circuit, then it is known as Eulerian graph. So what is a Euler path? A path in a graph G is called Euler path if it includes every edge exactly once. Since the path contains every edge exactly once, it is also called Euler trail. So trail was an open walk, isn't it? Euler circuit. An Euler path that is circuit is called Euler circuit. A graph which has a Eulerian circuit is called an Eulerian graph. So what was a circuit? Circuit was a closed walk. So let us see this example. Example 1 here. We get a Euler path from A to B, B to C, C to D, D to E and E to B. So in this way we get a Euler path which covers every edges, but the path is not closed. It's not a closed walk, so we'll not get a Euler circuit. Also, for a graph to be Eulerian graph, the vertices must be of even degree. Every vertices must. Here the vertices are even degree, but we will not obtain a Euler circuit since the Euler path is not closed, and hence example 1 is not a Euler graph. Since both the conditions Euler path and Euler circuit are not satisfied. At least one is satisfied, both are not satisfied. So in the second example, we see all the vertices are of even degree, so it can be a Euler graph. So first let us see if we get a Euler path. Okay, we get a Euler path covering all the edges without any repetition from A to B, B to D, D to F, F to G, E, again D, C, A. Vertex is repeated, but edge is not repeated. So we get a Euler path, and also the starting and the ending vertex is same, that is A. So it has got a closed walk and so Euler circuit, and hence both Euler path and Euler circuit is obtained for this example 2. Hence example 2 is an example of Euler graph. So now example 3, here we have let us name the vertices A, B, C, D and E. Here vertex E is of degree 4 and all other vertices A, B, C, D are of degree 1, so we cannot say it may or may not be a Euler graph. First let us check Euler path. So we will not get a Euler path since all the edges cannot be covered in a sequence, in a walk sequence. It's also not a closed path or a closed walk, so we cannot get Euler circuit, so it's not a Euler graph. Now let's see some examples of graphs. First example is of a graph which is both Eulerian and Hamiltonian. Here let us find a closed Euler path of the graph, given graph. The given graph has even degree in all its vertices. Okay, all the vertices have even degree, so it will obviously be Euler graph, but even then let us find a closed Euler path. A, E1, B, E2, C, E3, D, E4, A, E5, C, E6, then D, E7, B, E8, A. So here some of the vertices are repeated, but none of the edges are repeated. So it is a closed Euler path. So we will get a Euler circuit. Hence this graph is a Eulerian graph. Now let us check for Hamiltonian graph. Let us find a closed Hamiltonian path, that is a path where no vertices are repeated. So here we will get A, E1, B, E2, C, E3, D, E4, A. So this is a closed Hamiltonian path where the n vertices are repeated but none of the other vertices are repeated. So this is a Hamiltonian graph as well as Eulerian graph. Second example, Eulerian but not Hamiltonian. So first of all, let us find Eulerian path. Here all the vertices are of even degree, that is 2. Degree is 2 here. So closed Euler path, A to B, B to E, E to C, C to D, D to E, again E to A. So it is a closed Euler path and none of the edges are repeated. So it is a Euler graph. We will get a Euler circuit and it will be a Euler graph. Next, for Hamiltonian, let us check if there is a Hamiltonian path available in the graph. So from A to B, B to E, E to C, C to D. Okay, it's a Hamiltonian path covering all the vertices, but the path is not closed. Okay, so we'll not get a Hamiltonian circuit because circuit is a closed walk, but the Hamiltonian path we have acquired here is not closed. It's not closed, so this graph is Eulerian, but this graph is not Hamiltonian. So this is an example of Eulerian but not Hamiltonian graph. Next, question number 3 or example number 3, you can say Hamiltonian but not Eulerian. Here same thing, you have to see the vertices, degree of the vertices. So here all the vertices have odd degree, and vertices with odd degree are not Eulerian graphs. Here all the vertices have degree 3, that is odd. So this graph is obviously not a Eulerian graph. We are not required to find Eulerian circuit or Eulerian path. Even if we find, it will not be Eulerian graph and it will not be closed, main thing. Next, for Hamiltonian, let us check Hamiltonian path and if it is closed or open. So we'll start from the vertex A to B, B to C, C to D, D to F, F to E, E to H, H to G, again back G to A. So it is a Hamiltonian path and it is closed. All the vertices are covered, Hamiltonian path. The n vertices are repeated. All vertices are visited only once. Edges can be repeated for Hamiltonian path, but vertices should not be repeated. So this is an example of Hamiltonian graph but not Eulerian graph. Next, fourth example, neither Hamiltonian nor Eulerian graph. So let's check the graph. Here all the graphs are not of odd degree. The vertex D is of degree 1. So let us check if there is a Euler path and Hamiltonian path. So for Euler path, all the edges should be visited once. So D to C, C to A to B, B to C. Okay, it's a Euler path. All the edges are visited once, but it is not closed. If we again go from C to D, it will be closed, but the edge C to D will be visited twice, and it will not be Euler path then. So let us check Hamiltonian path. A to B, B to C, C to D. But that's not a closed Hamiltonian path. It's a Hamiltonian path, but because all the vertices are visited once, but it's not closed. Since it is not closed, so a Hamiltonian circuit will not be obtained. So thus, this is an example of neither Hamiltonian nor Eulerian graph. Hope you have understood what is a Hamiltonian and Eulerian graph. Thank you for watching the video.